NEC section 220.84 dictates that feeder ampacity must be determined according to Article 220, Part A, ensuring it adequately serves the total load. To calculate the necessary feeder size for the guardhouse, we must first determine the total load. The total load consists of the air conditioner, which is 1500 watts, the heater also 1500 watts, two ceiling lights at 100 watts each, totaling 200 watts, and a receptacle assumed at 100 watts. Adding these together, the total load is 1.5 kilowatts plus 1.5 kilowatts plus 0.2 kilowatts plus 0.1 kilowatts, which equals 3.3 kilowatts. To find the feeder ampacity at 240 volts, we divide the total load of 3.3 kilowatts by 240 volts, resulting in 13.75 amps. However, according to NEC section 215.2a3, we must account for continuous loads by multiplying the calculated ampacity by 1.25. Therefore, the minimum feeder ampacity is 13.75 amps times 1.25, which equals 17.2 amps. Now, let's determine the minimum feeder size. Based on table 310.15b16, the minimum conductor size for a 17.2 amp feeder is number 14 AWG. However, for underground installations, NEC section 300.5d requires conductors to be insulated for use in wet locations. Thus, number 14 AWG THWN or number 14 AWG XHHW conductors should be used. The proposed 40 amp 120/240 volt feeder with number 14 AWG THWN or XHHW conductors technically meets the NEC requirements for a feeder to the 6x10 guardhouse with the specified load requirements. This is because the conductors are protected at their ampacity. While number 14 AWG is rated for 15 amps in some instances, a 240 volt circuit requires overcurrent protection at 20 amps per NEC table 240.4d. The provided information states that the feeder should be protected by a 20 amp circuit breaker or fuse at the main service panel. There are also additional considerations. Firstly, a ground rod must be installed at the guardhouse location. Secondly, the feeder should be protected by a 20 amp circuit breaker or fuse at the main service panel. Thirdly, the guardhouse panel should be labeled to indicate the source of the power supply. When determining the appropriate feeder size and protection for an electrical installation, several critical factors must be considered beyond simply meeting the minimum calculated ampacity. It's essential to ensure that the selected conductors and overcurrent protection devices are appropriately sized and coordinated to provide adequate safety and prevent potential hazards such as overheating or electrical faults. Firstly, conductor ampacity must be carefully evaluated based on the specific conditions of the installation, including the ambient temperature, the number of conductors in a raceway or cable, and the type of insulation used. NEC Table 310.15b16 provides ampacity ratings for various conductor sizes and insulation types under specific conditions, but these ratings may need to be adjusted based on the actual installation environment. For example, if the conductors are installed in an area with high ambient temperatures, the ampacity may need to be derated to prevent overheating. Secondly, overcurrent protection devices, such as circuit breakers or fuses, must be selected with appropriate ampacity ratings to protect the conductors from overload and short-circuit conditions. The overcurrent protection device should be sized to protect the conductors in accordance with NEC section 240.4, which generally requires the overcurrent protection device to have an ampacity rating no greater than the allowable ampacity of the conductors being protected. Thirdly, voltage drop is another important consideration when determining feeder size, especially for longer runs. Voltage drop occurs when the voltage at the load end of the feeder is lower than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment to operate inefficiently or malfunction, and it can also lead to overheating of conductors and equipment. NEC section 215.2am provides guidelines for minimizing voltage drop in feeders, recommending that the voltage drop should not exceed 3% for power, heating, and lighting loads or 5% for feeders. Fourthly, grounding and bonding are essential for ensuring electrical safety and preventing shock hazards. A properly grounded and bonded electrical system provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protection devices to quickly trip and energize the circuit in the event of a ground fault. NEC Article 250 provides detailed requirements for grounding and bonding electrical systems, including the use of grounding electrodes, equipment grounding conductors, and bonding jumpers. Fifthly, compliance with all applicable codes and standards is crucial for ensuring the safety and legality of electrical installations. The NEC is the most widely adopted electrical code in the United States, and it provides comprehensive requirements for the design, installation, and maintenance of electrical systems. However, local codes and standards may also apply, and it's important to consult with local authorities and qualified professionals to ensure compliance with all applicable regulations. Sixthly, future load growth should be taken into account when determining feeder size. If there is a possibility that the load on the feeder may increase in the future, it's prudent to select conductors and overcurrent protection devices with sufficient capacity to accommodate the anticipated load growth. This can help avoid the need for costly and disruptive upgrades in the future. Seventhly, coordination with other electrical systems and equipment is essential for ensuring proper operation and safety. The feeder should be coordinated with other electrical systems such as lighting, HVAC, and fire alarm systems to ensure that they can operate safely and reliably without interfering with each other. The feeder should also be coordinated with the utility company's electrical grid to ensure that it can handle the load requirements of the building or facility. Eighthly, documentation and labeling are important for providing clear and accurate information about the electrical system to future users and maintenance personnel. The feeder should be clearly labeled to indicate its source, voltage, ampacity, and the loads it serves. The electrical panel should also be labeled to identify the circuit breakers or fuses that protect the feeder. Ninthly, qualified professionals should be involved in the design, installation, and inspection of electrical systems to ensure that they are safe, reliable, and compliant with all applicable codes and standards. Electrical work can be dangerous, and it's important to have qualified professionals with the knowledge, skills, and experience to perform the work safely and correctly. Tenthly, regular maintenance and inspection of electrical systems are essential for preventing problems and ensuring continued safety and reliability. The electrical systems should be inspected regularly for signs of wear, damage, or deterioration, and any problems should be promptly addressed. Maintenance tasks such as tightening connections, cleaning equipment, and testing overcurrent protection devices should be performed on a regular basis to ensure proper operation. 11thly, energy efficiency should be considered when selecting feeder size and designing electrical systems. By using energy-efficient conductors, equipment, and lighting, it's possible to reduce energy consumption and lower operating costs while also reducing the environmental impact of the electrical system. 12thly, safety precautions should be taken when working with electrical systems to prevent electrical shock, burns, and other injuries. Always to energize circuits before working on them, and use appropriate personal protective equipment such as gloves, eye protection, and insulated tools. 13thly, ongoing education and training are essential for keeping up with changes in electrical codes, standards, and technology. The electrical professionals should participate in continuing education programs to stay informed about the latest developments in the field and to maintain their skills and knowledge. 14thly, communication and collaboration among all stakeholders are crucial for ensuring the success of electrical projects. This includes the owner, architect, engineer, contractor, electrician, and inspector. By communicating effectively and collaborating closely, it's possible to avoid misunderstandings, resolve issues quickly, and ensure that the project is completed safely, on time, and within budget. 15thly, innovation and creativity should be encouraged in the design and implementation of electrical systems. By exploring new technologies and approaches, it's possible to develop more efficient, sustainable, and resilient electrical systems that meet the evolving needs of society. 16thly, ethical considerations should guide all aspects of electrical work, from design to installation to maintenance. Electrical professionals have a responsibility to act in the best interests of the public and to uphold the highest standards of integrity and professionalism. 17thly, risk management is an important part of electrical project management. This includes identifying potential risks, assessing their likelihood and impact, and developing strategies for mitigating or managing those risks. 18thly, quality control is essential for ensuring that electrical work is performed to the highest standards of workmanship. This includes inspecting materials and equipment, verifying that installations are performed correctly, and testing the completed system to ensure that it meets all applicable requirements. 19thly, sustainability should be a guiding principle in the design and operation of electrical systems. This includes using renewable energy sources, reducing energy consumption, minimizing waste, and protecting the environment. 20thly, resilience is an increasingly important consideration in the design of electrical systems. This includes designing systems that can withstand disruptions such as power outages, natural disasters, and cyber attacks, and that can quickly recover from such events. 21stly, accessibility should be considered in the design of electrical systems to ensure that they can be easily accessed and maintained by qualified personnel. This includes providing adequate clearances around equipment, using standardized components and connections, and providing clear and accurate documentation. 22ndly, aesthetics should be considered in the design of electrical systems to ensure that they are visually appealing and that they complement the overall design of the building or facility. This includes concealing wiring and equipment where possible, using attractive lighting fixtures, and coordinating the color and finish of electrical components with the surrounding environment. 23rdly, cost-effectiveness should be considered in the design of electrical systems. This includes evaluating the life cycle costs of different options, considering the initial cost, operating costs, maintenance costs, and replacement costs. 24thly, flexibility should be considered in the design of electrical systems to ensure that they can be easily adapted to changing needs and requirements. This includes using modular components, providing spare capacity, and designing systems that can be easily reconfigured or expanded. 25thly, reliability should be a primary consideration in the design of electrical systems. This includes using high-quality components, providing redundant systems, and designing systems that can operate safely and reliably under a wide range of conditions. Considering all these aspects ensures a safer and more effective electrical system.